The universe has no center, no edges, no directions, and it is actively expanding, pulling everything apart faster every second. If you were lost in deep space, you wouldn't just be lost the way you get lost on a road trip. You would be lost in a way that is permanent, total, and written into the laws of physics themselves. And the further we go, the more impossible going back becomes. And here is a question: if you could teleport anywhere in the universe, where would you explore first? Let me know in the comments. I will pin the most creative answer. Now let's begin. When you navigate anywhere on Earth, you're using them without even thinking about it. Street signs, mountain ranges, the angle of the sun. When sailors crossed oceans centuries ago, they used the stars. Specific stars, known stars, stars that held predictable positions in the sky because from our tiny corner of the galaxy, they barely seem to move at all. The North Star, Polaris, was a gift, a fixed anchor in a rotating sky. Navigation felt hard, but it was possible because the sky gave you something solid to hold on to. Now step outside the solar system, and I mean really step outside, like the Voyager 1 probe did when it crossed into interstellar space back in 2012, and suddenly everything you used to find your way starts to fall apart. Voyager 1 is the farthest human-made object from Earth. It launched in 1977. After nearly 5 decades of travel at speeds that would embarrass any aircraft ever built, it sits about 24 billion kilometers away. That sounds enormous, and by human standards it absolutely is. But in cosmic terms, it hasn't even left the immediate neighborhood of our solar system. It's like stepping off your porch and announcing you've seen the world. From Voyager 1's current position, the sun is still there, still visible, just tiny, a bright point among countless others. You could theoretically still trace a line back toward it. But here's where disorientation starts creeping in. The farther you travel, the more every star begins to resemble every other star. The sun, seen from just a few light years away, becomes nearly indistinguishable from the thousands of other yellow dwarf stars scattered across the galaxy. Without incredibly precise instruments and a preloaded star chart, you could not point to it and say with any confidence, "That one, that's mine." And we're still only talking about our immediate galactic backyard. Let's zoom out further, much further. Let's talk about the architecture of the universe itself, because this is where things stop being merely tricky and start becoming philosophically haunting. The universe isn't a random scattering of stars and galaxies thrown about like confetti. It has structure, vast, breathtaking, almost incomprehensible structure. Astronomers have spent decades mapping it, using surveys like the Sloan Digital Sky Survey, which spent years cataloging the positions of hundreds of millions of galaxies. What they found is something called the cosmic web, an enormous network of filaments, sheets and walls made of galaxies and dark matter, stretching across hundreds of millions of light years in every direction. These filaments meet at dense nodes called galaxy clusters. Between them lie enormous hollow regions known as cosmic voids. The Bootes void, for example, is a confirmed region of space roughly 330 million light-years across, and it contains almost nothing inside it, almost no galaxies, almost no stars, just an eerie, cavernous emptiness on a scale that the human mind genuinely struggles to process. Discovered in 1981 by astronomers Robert Kirshner and colleagues during a survey of galaxy redshifts, it remains one of the largest known voids in the observable universe. Now imagine you're drifting through one. You look in every direction, nothing. The cosmic web surrounds you, but you are deep inside a bubble of near-total emptiness so vast that light would take hundreds of millions of years just to cross it. No landmarks, no reference points, no nearby galaxies to triangulate from, just an ocean of nothing, and you at the center of it. This is not a thought experiment drawn from science fiction. This is a confirmed feature of the real universe. But wait, it gets considerably stranger. And this is where the cosmos really starts to play with your sense of reality. The universe is expanding, not just a little, dramatically. And here's the part that shook the entire scientific community when it was confirmed in 1998 by two independent teams studying distant supernovae. It's speeding up. Back in 1929, Edwin Hubble, working at the Mount Wilson Observatory in California, made one of the most transformative discoveries in scientific history. By measuring the light from distant galaxies, he found that almost all of them were moving away from us, not because they were flying through space from some central explosion point, but because space itself, the very fabric between them and us, was stretching. Every region of the universe was growing simultaneously in every direction. Think of it this way. Draw dots on the surface of a balloon. Now blow it up. Every single dot moves away from every other dot, not because the dots themselves are traveling, but because the surface between them is expanding. There is no center dot. No dot is more in the middle than any other. They all move apart equally. The universe works the same way, just in 3 dimensions, and on a scale that collapses human intuition entirely. The rate of this expansion is captured in something called the Hubble constant, currently estimated at around 70 kilometers per second per megaparsec. In plain language, for every 3.3 million light-years of distance between two objects, the space between them is growing by about 70 kilometers every single second. Over truly vast distances, that accumulates fast. Some galaxies are effectively receding from us faster than the speed of light, not by breaking any physical law, but because there is simply so much expanding space between us and them that the cumulative stretch exceeds light speed, and that means they're gone, unreachable, not temporarily, permanently. There is a boundary surrounding us called the cosmic event horizon, the limit beyond which objects are receding so rapidly that light from them can never, under any circumstances, reach us again. Anything beyond that line is cut off. If you somehow traveled out past it, you could never return, not because of any wall or barrier, but because the universe itself would be expanding away from your destination faster than you could ever chase it. That is not a metaphor or an approximation. That is what the physics tells us. So let's take stock of what we now know. The universe has enormous, web-like structure, filaments, voids, and galaxy clusters woven together across hundreds of millions of light-years. It's expanding, and that expansion is accelerating. Beyond a certain distance, nothing, not a signal, not a spacecraft, not even light itself, can make the return journey. But here's the detail that truly keeps cosmologists lying awake at 3 in the morning. We don't actually know how large the universe is. We only know the size of the observable universe, the portion we can see, limited by how far light has had time to travel since the Big Bang, roughly 13.8 billion years ago. The observable universe extends about 46 billion light-years in every direction from where we stand, larger than the age of the universe in light-years, because of all that expansion happening the whole time. But beyond that horizon, beyond the edge of what we can observe, we have absolutely no idea what lies there. The universe could be thousands of times larger than the portion we see. Some models in cosmology suggest it could be effectively infinite. Right now, with every telescope and instrument available to us, we genuinely cannot say. And if it's infinite, then home isn't just difficult to find. It's an infinitely small point in an infinite expanse. Let that sit for a moment. Here's something that sounds like it came straight out of a philosophy class, but is actually one of the most rigorously tested conclusions in all of modern science. There is no center to the universe. Not we haven't found it yet, not it's somewhere we can't reach. Literally, there is no center, no special point in space from which everything else fans outward, no cosmic ground zero. Every single location in the universe is, in a deeply meaningful sense, equivalent to every other. And if you're thinking that sounds impossible, that something has to be at the middle, then your instincts are working perfectly, because they were shaped by a lifetime of living on a planet with very clear centers, edges, and directions. The cosmos, it turns out, didn't get that memo. Let's go back to Edwin Hubble for a moment, because his discovery didn't just tell us the universe was expanding. It quietly demolished something we had assumed for thousands of years, that we occupy a privileged position in space. When Hubble mapped the recession of galaxies in 1929, he found something that initially looked suspicious. Every galaxy, in every direction, was moving away from us. At first glance, that sounds like we're at the middle of everything, right? Like we're standing at the center of some enormous explosion and watching the shrapnel fly outward in all directions. But that balloon analogy from part 1 is key here. When the balloon expands, every dot on its surface moves away from every other dot simultaneously. There is no dot that sits at the center of the expansion. There is no privileged position. If you were an ant living on one of those dots, and you could somehow observe the other dots moving away from you in every direction, you might also conclude, incorrectly, that you must be at the center. But so would every other ant on every other dot. They would all be right, and they would all be wrong at the same time. That is the actual structure of our universe. The technical term for this is the cosmological principle, and it's one of the foundational assumptions of modern cosmology, verified repeatedly by large-scale surveys of the sky. It states that, on the largest scales, the universe is both homogeneous, meaning roughly the same in terms of matter density and composition everywhere, and isotropic, meaning it looks the same in every direction. No location is special. No direction is preferred. The universe has no edges, no walls, no center, and no outside. Now let's really let that sink in. Because what it means for navigation is devastating. When you navigate on Earth, you orient yourself relative to something. Landmarks, cardinal directions, GPS satellites triangulating your position from known fixed reference points. Even when sailors crossed oceans by starlight, the stars themselves served as fixed reference points, distant but dependable anchors in the sky. In deep space, the cosmological principle strips all of that away. There is no cosmic north, no galactic true south, no fixed frame of reference against which all positions can be measured. Everything is moving relative to everything else, and because the universe has no center and no edges, there is no absolute background grid you can compare yourself against. Physicists call this the problem of absolute position. You can describe where you are relative to something nearby, a particular star, a galaxy cluster, but you cannot describe where you are in any absolute cosmic sense. The universe simply doesn't offer that kind of information. It's not hidden or encoded somewhere, waiting to be discovered. It genuinely doesn't exist. Now here's where this gets visceral. Imagine you fall asleep on a spacecraft, maybe due to some malfunction, and you wake up somewhere in deep space with no memory of how far you traveled or in which direction. You look out the window, stars everywhere, beautiful but anonymous. How do you begin? Well, you might try to identify known star patterns, constellations, but constellations, as we see them from Earth, are an illusion of perspective. Orion, for example, looks like a coherent pattern from our solar system, but the stars that form it are at wildly different distances from us. Betelgeuse sits about 700 light-years away. Rigel is around 860 light-years. Bellatrix is only about 250, from even a relatively small displacement in space. Those stars shift in apparent position dramatically, and the familiar shape dissolves. Orion ceases to exist. Every constellation you've ever known would shatter into noise. You could try to look for the Milky Way, and yes, from within the local group of galaxies, it would still be identifiable. a barred spiral galaxy, roughly 100,000 light-years in diameter, our cosmic home. But here's the problem. The universe contains an estimated 2 trillion galaxies, revised upward dramatically in 2016 when a team led by astronomer Christopher Consolis at the University of Nottingham reanalyzed deep-field images from the Hubble Space Telescope. Many of those galaxies are barred spirals. Many look remarkably similar to ours from a distance, without a pre-existing, extraordinarily detailed star map and precision instruments capable of measuring distances down to the light year. Identifying the Milky Way from outside the local group would be, by any practical standard, impossible. And if you're deep enough in space, hundreds of millions of light years out, the Milky Way would simply not be visible at all. It would be too faint, too distant, swallowed entirely by the dark. Now, right here, I want to pause and say something directly to you. If this kind of content lights something up in your brain, if you find yourself leaning forward, thinking harder, feeling that quiet electricity that comes from genuinely wrestling with big ideas, then subscribe to this channel and hit that like button. It genuinely helps me reach more curious people just like you, and it's the single best way to let me know you want more of this. We're building something here, a community of people who look up at the sky and refuse to stop asking questions. I would love for you to be part of it. All right, back to the abyss. So we've established that there is no center, no privileged position, no absolute frame of reference, and no constellation map that survives any significant displacement in space. But there's another navigational tool you might think of, one that sounds promising at first. Pulsars. Pulsars are a type of neutron star, the collapsed core of a massive star that exploded as a supernova. They spin at extraordinary rates and emit beams of electromagnetic radiation from their magnetic poles. Because the star is rotating, those beams sweep through space like a cosmic lighthouse, reaching us as precise, rhythmic pulses of radio waves. Some pulsars pulse hundreds of times per second. Their timing is so reliable that they rival atomic clocks in their precision. Here's the fascinating part. Scientists designing the Pioneer 10 and Pioneer 11 spacecraft, launched in 1972 and 1973, included a gold-anodized aluminum plaque on each one, partly as a message to any extraterrestrial intelligence that might intercept them, and to help any hypothetical finder figure out where the probes came from. The plaque included a pulsar map, a diagram showing the relative positions and pulse frequencies of 14 specific pulsars, with lines radiating from a central point representing our solar system. The idea was elegant. Pulsars are unique. Their pulse rates change very slowly and predictably over time, so any sufficiently advanced civilization could use them as a cosmic coordinate system, a kind of three-dimensional lighthouse grid spanning the galaxy. This concept was extended on the Voyager Golden Records, also crafted with significant input from Carl Sagan, which included a more refined pulsar map designed to triangulate our precise position in the Milky Way. It's a beautiful idea. And it works, in theory, if a few critical conditions are met. You need to already have a comprehensive map of pulsar locations and pulse rates. You need instruments capable of detecting and precisely measuring them, and you need enough pulsars in view to triangulate from. In certain regions of deep space, far from the galactic plane, far from the dense stellar nurseries where neutron stars are most common, pulsars become increasingly sparse. Their signals, already faint across thousands of light years, become even harder to isolate and identify. More critically, pulsars are distributed within the Milky Way. They're a tool for navigating within our galaxy and perhaps within our local group. Step outside that context entirely, drift into the cosmic voids between galaxy clusters, and even the pulsar grid fades to silence. But the pulsar navigation concept has had real, modern applications. In 2017, NASA tested something called NISA, the Neutron Star Interior Composition Explorer, mounted on the International Space Station, partly to investigate the possibility of using pulsars as a real-time autonomous navigation system for deep space missions. The idea is sometimes called the Galactic Positioning System, or GPS, a deliberate nod to the satellite navigation we rely on daily. Early results were genuinely promising for navigating within the inner solar system and nearby interstellar space. But the limitations at truly cosmic distances remain formidable, and here's what all of this is quietly pointing toward. Every navigation system we have ever devised, from ancient star charts to pulsars to GPS satellites, relies on having a known map, a pre-existing catalogue of reference points with understood positions, distances, and behaviors. Navigation, at its heart, is not about finding your way in the unknown. It is about relating your unknown position to a known one. In deep space, truly deep space, you eventually run out of known positions. You reach the edge of your map, and beyond that edge, there is simply no reference frame to anchor yourself to. No north, no center, no familiar lighthouse blinking in the dark. You are, in the most complete sense of the word, lost. And yet, and this is the part that fills me with something I can only describe as awe mixed with vertigo, we are here. On this pale blue dot, as Carl Sagan so etchingly described it, we have built telescopes that peer back nearly to the beginning of time. We have sent probes to the edges of the solar system. We have mapped hundreds of millions of galaxies. We have uncovered the cosmic web. We have measured the expansion of the universe to extraordinary precision. We are a species of beings made from atoms forged in dead stars, creatures who emerged from the same cosmic process that built the galaxies, and we looked up, and we wondered, and we refused to stop. That, to me, is one of the most extraordinary facts about reality. If you're enjoying this so far, make sure to subscribe to the channel. You will be joining a community of people who refuse to stop asking the big questions. Now let's talk about time. And I don't mean time in the way you usually think about it. The steady, reliable tick of a clock on your wall, the rhythm of days and nights, the calendar on your phone telling you what month it is. I mean time as the universe actually behaves it. Because here's something that took physicists the better part of the 20th century to fully come to terms with, and that most of us still haven't genuinely absorbed at a gut level. Time is not fixed. It is not the same everywhere. It does not flow at a constant rate across the universe. It bends, stretches, and slows depending on where you are and how fast you're moving. And the moment you start traveling through deep space, truly deep space, at the kinds of speeds a hypothetical interstellar journey would require, time becomes one of the most disorienting and treacherous forces you will ever encounter. This isn't speculation. It isn't a theoretical curiosity tucked away in academic journals. It is one of the most thoroughly tested and confirmed discoveries in the history of science. And it comes from a man who, in 1905, published 4 papers that together rewired humanity's understanding of physical reality. His name, of course, was Albert Einstein. Einstein's special theory of relativity introduced the world to a concept called time dilation. The core idea sounds simple, almost too simple, until you follow it to its conclusions. The faster you move through space, the slower time passes for you relative to someone who is stationary. Not as a feeling, not as a psychological trick, as a measurable, physical, real difference in the actual rate at which time flows. We test this constantly, right here on Earth. The GPS satellites orbiting our planet have to account for relativistic time dilation in their onboard clocks, both because of their speed and because of the weaker gravitational field at their altitude. If engineers didn't correct for these effects, GPS navigation would drift by several kilometers per day. The math of relativity is baked into the technology sitting in your pocket, but those are tiny corrections, fractions of microseconds. The effects are real but imperceptible to human experience at everyday speeds. Now take those same equations and scale them up to the velocities required for interstellar travel, and the numbers become genuinely staggering. Let's say you board a spacecraft capable of traveling at 90% of the speed of light. That's roughly 270 million meters per second, a speed so far beyond anything we've ever built that it might as well be magic for now, but physically it doesn't violate any known law. At 90% of light speed, the time dilation factor, called the Lorentz factor, after the Dutch physicist Hendrik Lorentz, who first worked out the mathematics, means that for every roughly 2.3 years that pass aboard your ship, about 5 years pass back on Earth. Push that to 99% of light speed, and the gap widens dramatically. For every year you experience on the spacecraft, about 7 years tick by back home. At 99.9% of light speed, 1 year aboard the ship corresponds to roughly 22 years on Earth. And at the extreme hypothetical edge, if you could somehow reach 99.9999% of light speed, a single year of your experience could correspond to over 700 years passing back on Earth. Now freeze on that image for a moment. You leave, you travel, you feel, from your own perspective inside the ship, that a reasonable amount of time has passed. You turn around and head back. You return to what you believe is home, and you step out to find that centuries have elapsed. Everyone you knew is gone. The language may have shifted. The civilization may be unrecognizable. The city you grew up in may not exist in any form you would recognize. Is that home? Can it still be called that? This is not a science fiction plot twist. This is what the physics of the universe actually prescribes. Time dilation is not a loophole or an edge case. It is a fundamental feature of the fabric of reality, as dependable and inescapable as gravity. And speaking of gravity, Einstein didn't stop with special relativity. In 1915, he published the general theory of relativity, extending his framework to include acceleration and gravity. And what he found was that gravity doesn't just pull objects, it curves space-time itself. Mass warps the geometry of space and time around it. The way a heavy ball placed on a stretched rubber sheet creates a depression that nearby objects roll toward. One of the consequences of this is gravitational time dilation. The stronger the gravitational field you're in, the slower time passes for you relative to someone in a weaker field. Clocks at sea level on Earth tick ever so slightly slower than clocks on a mountaintop because sea level is deeper inside Earth's gravitational well. The difference is tiny here, but near a massive object it becomes extreme. Near a neutron star, one of those collapsed stellar cores we talked about in Part 2, the surface gravity is so intense that time genuinely crawls compared to the rest of the universe. And near a black hole, the effect becomes total. At the event horizon, the point of no return around a black hole, time, as experienced by an outside observer, appears to freeze entirely. An astronaut falling toward it, from their own perspective, would cross the horizon in a finite amount of time. But to anyone watching from a safe distance, they would appear to slow down and stop, like a film gradually losing its frames. In 2014, the film Interstellar famously depicted a planet orbiting very close to a massive black hole, where 1 hour on the surface corresponded to 7 years back on Earth. Christopher Nolan worked closely with the theoretical physicist Kip Thorne, who would go on to win the Nobel Prize in Physics in 2017 for his role in detecting gravitational waves, to get the physics as accurate as possible. The result was one of the most scientifically grounded portrayals of relativistic time dilation ever put on film. But let's bring this back to our central question: finding your way home in deep space. Imagine you've been traveling for what feels to you like several years. You've navigated through the dark as best you can, using pulsar signals, stellar maps, whatever instruments you have available. You believe you've found your way back toward the Milky Way. You're oriented, or as close to oriented as the cosmos allows. You are going home, but how long have you actually been gone? Not from your perspective, from Earth's perspective. If you traveled at a significant fraction of the speed of light, even if you did everything perfectly, even if your navigation was flawless, you would have no reliable way of knowing how much time had elapsed back home without a prior agreement and extraordinarily precise communication. The two timelines, yours and Earth's, would have diverged the moment you left, silently and irrevocably, at a rate determined entirely by your velocity and the gravitational fields you passed through. This is what physicists call the twin paradox, though it's not really a paradox at all, just a deeply counterintuitive consequence of relativity that resolves cleanly once you work through the math. Two twins, one stays on Earth, one travels near light speed and returns. The traveling twin comes back younger, not metaphorically, biologically, measurably younger. Fewer heartbeats have passed, fewer cellular divisions, less aging at the molecular level. The universe offers no override for this, no way to resynchronize after the fact. The gap is permanent, so now add this layer to everything we explored in parts 1 and 2. You have no center to navigate from. Your constellations have dissolved with distance. Your pulsar map has its limits. And now, even if you somehow found your way back to the right neighborhood, the when of your arrival is as uncertain as the where. You return to a coordinate in space, only to find that time has deposited you into a version of home that may be decades or centuries removed from the one you left. The universe doesn't just scramble your map, it scrambles your calendar. And yet, this is the part I genuinely find breathtaking. These same phenomena that make homecoming so impossible are also what make the cosmos so astonishing to explore. Time dilation means that in principle, a human being could travel to distant parts of the galaxy within a single lifetime. If the spacecraft were fast enough, the rest of humanity would age and change and evolve while you crossed the stars. But you could do it. You could, with the right technology, watch the Andromeda galaxy approach and swell in your window, knowing that you left Earth as a child and could return, if the physics permitted, as an old person to a civilization thousands of years evolved beyond the one you knew. We are not just passengers on a rock circling a star. We are embedded in a universe where time itself is a landscape, curved, warped, and magnificent, where the same forces that make it impossible to come home are the ones that make the journey incomprehensibly, staggeringly vast. There's a quote from Einstein that I think about often. He said, and I'm paraphrasing slightly, that the most beautiful thing we can experience is the mysterious, that it is the source of all true art and science. He who can no longer feel that wonder, he said, is as good as dead. I think about that when I think about time dilation, because here is a man who sat with a pencil and paper, who thought hard and honestly about what light and motion and time really meant, and in doing so, he didn't just solve equations. He cracked open the universe and showed us that reality is incomparably stranger and more beautiful than anything our intuitions had prepared us for. We are made of atoms that were forged in the cores of stars that died long before our sun was born. We are, in the most literal possible sense, children of deep time, and the fact that we can measure it, model it, and feel something like wonder in its presence, that is to me one of the most extraordinary things about being alive. Let's start with a number, 5%. That is the fraction of the universe that is made of ordinary matter, the stuff you can see, touch, measure, and interact with. Protons, neutrons, electrons, atoms, molecules, every star you've ever looked at, every planet ever discovered, every ocean, every mountain, every living creature that has ever existed on this earth, every spacecraft we have ever launched, every telescope we have ever built, every photon of light that has ever traveled across the cosmos, and landed on a human retina, all of it, every single bit of it, adds up to roughly 5% of what the universe actually contains. The other 95%, we don't fully know what it is. About 27% of the universe appears to be something physicists call dark matter. Another 68% is something even stranger, dark energy. And before you dismiss those as placeholder names for things we'll figure out soon, understand this. We have been working on these problems seriously since the 1930s, and in the decades since, despite some of the most sophisticated experiments ever designed by human beings, the fundamental nature of both remains genuinely, deeply unknown. This is not a gap at the fringes of knowledge. This is a gaping hole at the very center of our understanding of the cosmos. And it matters enormously for the question of whether you could ever find your way home in deep space, because dark matter and dark energy are not passive background characters in the story of the universe. They are the primary architects of its structure and its fate. Let's take dark matter first, because its story is one of the most compelling detective narratives in all of science. In the 1930s, a Swiss astronomer named Fritz Zwicky was studying the Coma cluster, a large galaxy cluster about 330 million light-years away from us. He was measuring the velocities of galaxies within the cluster, expecting them to behave the way any gravitationally bound system should. Objects on the outer edges of such a cluster should move more slowly than those near the center, just as the outer planets of our solar system orbit the Sun more slowly than the inner ones. That's Newtonian gravity, straightforward and reliable, but the galaxies in the Coma cluster weren't behaving that way. They were moving far too fast, so fast in fact that by any ordinary calculation, the cluster shouldn't hold together at all. The visible matter, all those billions of stars in hundreds of galaxies, didn't provide nearly enough gravitational pull to keep the whole thing from flying apart. Zwicky proposed that there must be additional, invisible mass present, matter that wasn't emitting or reflecting any light, but whose gravity was holding the cluster together. He called it Dunkel Materiae, dark matter. His colleagues largely ignored him for decades. Then, in the 1960s and 70s, an American astronomer named Vera Rubin, working with her colleague Kent Ford, began measuring the rotation curves of spiral galaxies. The prediction was the same as Zwicky's. Stars near the outer edges of a spinning galaxy should orbit the galactic center more slowly than stars near the middle. Less mass nearby means less gravitational pull, means slower orbital speed. Simple, except that wasn't what Rubin found. At all outer stars in spiral galaxies were orbiting at roughly the same speed as inner stars, sometimes even faster. The rotation curves were flat when they should have been declining. Rubin analyzed galaxy after galaxy and found the same result every time. The only explanation that fit the data was that each galaxy was embedded in an enormous halo of invisible mass, matter that extended far beyond the visible edges of the galaxy, providing the gravitational scaffolding that kept the whole spinning structure from tearing itself apart. This was the modern confirmation of dark matter, not as a fringe idea, but as an observational necessity. Vera Rubin's work was meticulous, reproducible, and undeniable. She spent years facing skepticism and dismissal in a field that was still, in those decades, deeply unwelcoming to women. But the data held. The universe was telling us something, and she was listening. Today, the evidence for dark matter is overwhelming and comes from multiple independent directions. The cosmic microwave background, the faint afterglow of the Big Bang, mapped in extraordinary detail by the Planck satellite with final results published in 2018, encodes the signature of dark matter in the precise pattern of its temperature fluctuations. Gravitational lensing, where massive objects bend light passing near them like a cosmic lens, reveals dark matter halos around galaxy clusters that are far more massive than the visible galaxies themselves. The Bullet cluster, actually a pair of colliding galaxy clusters about 3.8 billion light-years away, provided one of the most direct pieces of evidence yet, showing through X-ray observations and gravitational lensing that the dark matter in the collision passed straight through while the hot gas, ordinary matter, was slowed down. The dark matter and the visible matter separated, like two different crowds walking through each other. But here is what we still don't know: what dark matter actually is. The leading candidates are hypothetical particles called WIMPs, weakly interacting massive particles, which would interact with ordinary matter only through gravity and the weak nuclear force, making them essentially invisible to every conventional detector. Enormous experiments have been built specifically to catch them, deep underground to shield out cosmic radiation, filled with ultra-pure materials designed to detect the faint recoil of a dark matter particle striking an atomic nucleus. The Lux Zeppelin experiment in the Sanford Underground Research Facility in South Dakota, currently one of the most sensitive dark matter detectors ever built, has been running without detecting a confirmed WIMP signal. Other experiments around the world, Panda X in China, Xenont in Italy, have similarly come up empty. That doesn't mean dark matter doesn't exist. The gravitational evidence for it is ironclad. It means we may have been looking for the wrong kind of particle, or with the wrong kind of detector, or that dark matter consists of something we haven't fully theorized yet. Some physicists have proposed alternatives: axions, sterile neutrinos, primordial black holes, each with their own theoretical motivations and their own ongoing search programs. The James Webb Space Telescope, launched in December 2021 and now delivering images of unprecedented depth and clarity, is contributing to dark matter research by allowing us to map gravitational lensing effects with greater precision than ever before. The honest answer, as of right now, is that we don't know what dark matter is. And that is one of the most exciting statements in all of science. Now let's talk about dark energy. And this is where things escalate from mysterious to genuinely mind-bending. Cast your mind back to 1998. Two independent teams of astronomers, the Supernova Cosmology Project and the High Z Supernova Search Team, were doing something that sounds unglamorous but turned out to be revolutionary. They were measuring the brightness of a specific type of exploding star called a type supernova at enormous distances from Earth. Type Ia supernovae are extraordinarily useful to cosmologists because they all explode with roughly the same intrinsic luminosity. This makes them what astronomers call standard candles, objects whose true brightness is known, so that by measuring how bright they appear in the sky, you can calculate how far away they are. They are, in effect, mile markers on the cosmic highway. Both teams were using these supernovae to measure how the expansion of the universe had changed over time. The widely held expectation, based on everything scientists understood at the time, was that the expansion would be slowing down. Gravity, after all, is attractive. All the matter in the universe is pulling on all the other matter. It seemed obvious that this gravitational attraction would gradually put the brakes on the expansion that had been happening since the Big Bang. What both teams actually found, independently and to their own initial disbelief, was the exact opposite. The expansion of the universe is speeding up. The distant supernovae were dimmer than expected, meaning they were farther away than the models predicted, not closer, farther. The universe wasn't decelerating under gravity's pull. It was accelerating, driven by some kind of energy embedded in the fabric of space itself, an energy that acts in direct opposition to gravity, pushing space apart rather than pulling it together. This discovery was so stunning, so completely unexpected, and so thoroughly confirmed by subsequent observations that it earned the Nobel Prize in Physics in 2011, shared between Saul Perlmutter, Brian Schmidt, and Adam Riess, the leaders of those two competing supernova teams. Whatever is causing this acceleration, physicists named it dark energy. And here is the unsettling thing about it. Unlike dark matter, which at least behaves like matter, clumping under gravity, forming halos, leaving structural imprints we can map, dark energy appears to be uniformly distributed throughout all of space, with a constant density that doesn't dilute as the universe expands. In fact, as the universe grows larger, there is simply more space, and therefore more dark energy, and therefore the acceleration is growing stronger over time. The most mathematically natural explanation for dark energy is something Einstein actually proposed and then famously abandoned: a cosmological constant, a term he added to his equations of general relativity in 1917 to describe a static universe, which was the prevailing assumption before Hubble showed otherwise. Einstein called it his greatest blunder when expansion was confirmed. Decades after his death, the universe revealed that he may not have been wrong, just ahead of the data. But even calling it a cosmological constant is really just giving a name to our ignorance. We know how dark energy behaves. Its effect on the expansion rate is well measured. We know roughly how much of it there is. About 68% of the total energy content of the universe. We do not know what it fundamentally is, where it comes from, or whether it will remain constant into the future. Some models suggest it could decay over time, eventually reversing the acceleration. Others suggest it could grow stronger in a scenario called the Big Rip, eventually overcoming not just gravity, but all the fundamental forces, tearing apart first galaxy clusters, then galaxies, then solar systems, then planets, then atoms themselves, in a final catastrophic dissolution of all structure in the cosmos. Current data favors a roughly constant dark energy density, but the error bars are still wide enough that more dramatic scenarios cannot be fully ruled out. Now bring all of this back to our lost traveler in deep space. You are trying to find your way home. You have no center to navigate from. Your constellations have dissolved. Time has bent around your velocity. And now, underneath everything, the very fabric of space through which you are trying to navigate is being stretched by a force you cannot see, cannot measure directly, and cannot counteract. Every second you spend trying to find your bearings, dark energy is quietly expanding the distances between you and every reference point you might hope to use. The cosmic web itself, those great filaments and clusters that give the universe its large-scale structure, is slowly being pulled apart at its most diffuse edges, the voids between clusters growing wider with every passing moment. And the dark matter halos that envelop galaxies and galaxy clusters, halos you cannot see, are warping the paths of light itself across the universe. The light you receive from distant objects has been bent, stretched, and distorted by dark matter you will never directly detect. Your instruments, as sophisticated as they might be, are reading a universe shaped in large part by forces they cannot directly observe. You are navigating through a landscape where 95% of the terrain is invisible, where the floor is expanding beneath your feet, and where the light guiding you has been subtly bent by forces that leave no visible trace. And yet, here we are, here you are, watching this, thinking about it, feeling something stir. Because the fact that we live inside this mystery and can name it, can measure its effects, can stand at the edge of our knowledge and say honestly, we don't know what this is, but we are going to find out, that is something remarkable. Vera Rubin sat in her office and looked at rotation curves that didn't make sense and didn't look away. She leaned in, and in doing so, she helped map the invisible skeleton of the cosmos. We are a species that maps what it cannot see. That is not nothing. That is, in fact, everything. There is a question that has haunted philosophers, theologians, and scientists for as long as human beings have been capable of asking it. Why is there something rather than nothing? Why does a universe exist at all? Why does it have the specific laws it has, the precise values of gravity, electromagnetism, the strength of the nuclear forces, values that, if tweaked even slightly, would produce a cosmos where stars couldn't form, atoms couldn't hold together, and life of any kind would be utterly impossible? Why does the universe appear, in some deep and almost suspicious way, to be fine-tuned for complexity? For a long time, those questions lived exclusively in the domain of philosophy and religion. Science, it seemed, could describe how the universe works, but the question of why it exists at all, and why it works the way it does, felt permanently beyond its reach. Then cosmologists started doing their math more carefully, and some of them arrived at a conclusion that is either one of the most profound ideas in the history of human thought, or one of the most controversial. Possibly both. What if our universe isn't the only one? What if the Big Bang that created everything we know was not a singular, unique event, but one of an unimaginable number of similar events, each producing its own separate universe, each potentially governed by its own set of physical laws, its own constants, its own structure? What if the cosmos we inhabit is not the universe, but merely a universe, one bubble in a vast, perhaps infinite, churning sea of other bubbles, each one completely isolated from all the others, each one a world unto itself? This idea goes by several names: the many worlds interpretation, the megaverse, the landscape, most commonly the multiverse. And here is the crucial thing to understand before we go any further. The multiverse is not science fiction. It is not a fringe concept invented by writers looking for interesting plot devices. It emerges independently and somewhat inevitably from multiple serious lines of cutting-edge theoretical physics. It is taken seriously by some of the most rigorous and respected minds in cosmology. It is also deeply controversial because it pushes right up against the boundary of what science can currently test. But it is a legitimate area of active scientific inquiry, and understanding why it arises tells us something profound about the nature of the universe we actually live in. Let's start with the version that grows most naturally out of what we already know. Remember inflation, the theory that in the first tiny fraction of a second after the Big Bang, the universe underwent an extraordinarily rapid expansion, growing from something smaller than a subatomic particle to roughly the size of a grapefruit in an almost incomprehensibly brief moment. Inflation was proposed in 1980 by the physicist Alan Guth, then at the Stanford Linear Accelerator Center, as a way of explaining several puzzling features of the observable universe: why it looks so uniform in temperature in all directions, why its geometry appears so nearly flat, and why we don't see certain exotic particles that early universe physics predicted, but observations never found. Inflation solved all of those problems beautifully, and its core predictions have been confirmed repeatedly by observations of the cosmic microwave background, most recently and precisely by the Planck satellite. The broad strokes of inflation are now part of mainstream cosmological thinking, but here is what Guth and others discovered when they examined the mathematics of inflation more carefully. Once inflation starts, it is extraordinarily difficult to stop, everywhere, all at once. The quantum field that drives inflation, sometimes called the inflaton field, is subject to quantum fluctuations. In most regions of space, those fluctuations cause inflation to eventually end, producing a universe like ours. But in other regions, the fluctuations sustain the inflationary process, causing space to keep expanding at that explosive rate. And because inflating space expands so rapidly, those regions where inflation continues always outpace the regions where it ends, meaning inflationary space is always producing more of itself than it loses to universe creation. This process has a name: eternal inflation. and its implication is staggering. If eternal inflation is correct, then our Big Bang was not a unique event. It was one of an endless series of bubble nucleation events, moments where inflation ended in a particular region and a new universe crystallized out with its own physical constants, its own geometry, its own history. Each bubble is a separate universe, expanding away from all the others, causally disconnected, meaning no signal, no light, no particle, and no information of any kind can ever pass between them. They are not just distant, they are permanently and fundamentally unreachable. The physicist André Linde at Stanford University has been one of the primary architects of the eternal inflation framework, and he has described it in terms that capture both its grandeur and its strangeness. The universe we see, he has suggested, may be more like a single grain of sand on an infinite beach than a standalone creation. Now here is where this connects to the question of physical laws and to something called the string theory landscape. String theory, the theoretical framework that attempts to unify quantum mechanics and general relativity by proposing that the fundamental constituents of reality are not point particles but tiny, vibrating strings of energy, predicts an almost unimaginably large number of possible vacuum states. Each vacuum state corresponds to a different configuration of the compact extra dimensions that string theory requires, and each configuration produces a universe with different values for its physical constants, different strengths of gravity, different masses for elementary particles, different values for the cosmological constant, that dark energy term we talked about in Part 4. The number of possible vacuum states in string theory is estimated at around 10 to the power of 500. That is not 10,000, that is not 10 million. That is a 1 followed by 500 zeros, a number so incomprehensibly vast that it makes the total number of atoms in the observable universe look like a rounding error. If each of those vacuum states corresponds to a real universe somewhere in the eternal inflation landscape, then the question of why our universe has the particular physical constants it does gets a startling answer. Not because those constants were chosen, designed, or fine-tuned by any external agency, but because in a landscape of 10 to the 500th power universes, every possible combination of constants will exist somewhere, and we, by necessity, find ourselves in one of the subset of universes where the constants permit the existence of stars, planets, chemistry, and observers capable of asking the question, if the constants were different, we wouldn't be here to wonder about them. This line of reasoning is called the anthropic principle, and it is as philosophically contentious as anything in modern science. Critics argue with genuine force that a theory that can explain any observations by saying, well, we had to end up in a universe where that's true, is not really making testable predictions at all. Science, in its most rigorous sense, requires the possibility of being proven wrong. A multiverse that is causally disconnected from our own, unreachable by any conceivable experiment, is, by that standard, more metaphysics than physics. The physicist Paul Steinhardt, one of the original contributors to inflationary cosmology, who later became one of its most articulate critics, has argued that eternal inflation and the string landscape together produce a framework so flexible that it can accommodate essentially any observation, and that this flexibility is a scientific weakness rather than a strength. He and Neil Turok proposed an alternative, the cyclic cosmology model, based on collisions between higher dimensional structures called branes, that avoids eternal inflation entirely. The debate between these frameworks is ongoing, respectful, and unresolved. What all sides agree on is this: we do not yet have a confirmed, experimentally validated theory of what happened at or before the Big Bang, or of whether anything exists beyond our observable cosmic horizon. The multiverse is a serious hypothesis supported by serious mathematics. It is not confirmed. It may never be directly confirmable with any technology we can currently imagine. And yet, and this is what makes the science so electrically alive, there may be indirect ways to probe it. If two bubble universes in the eternal inflation landscape ever collided in the very early history of our universe, that collision might have left a faint imprint on the cosmic microwave background, a subtle circular pattern in the temperature fluctuations. Cosmologists have actually searched for exactly this signature in the Planck satellite data. The results so far are inconclusive. No confirmed collision signature has been found, but the search continues, and future experiments may reach the sensitivity required. The Simons Observatory in Chile, currently under construction, and the proposed CMB-S4 experiment, a next-generation ground-based telescope array, will map the cosmic microwave background with unprecedented precision, potentially opening windows onto the very earliest moments of our universe's existence and, perhaps, just perhaps, whispering something about what lies beyond it. Now let's bring all of this back to our lost traveler one more time. You are floating in deep space. You have no center, no constellations, no reliable time reference, no visible dark matter or dark energy. And now, if the multiverse is real, you face the ultimate navigational impossibility. You are not just lost within a universe, you are lost within one universe out of an effectively infinite number of universes. The very concept of home, of a specific place you came from and could return to, exists only within the bubble you were born in. Step outside it, and there is no outside, not in any direction you could point to, not in any dimension you could travel through. The other universes, if they exist, are not somewhere else in space. They are beyond space as we understand it. Separated not by distance, but by the fundamental structure of reality itself. There is no map that covers that territory. There is no compass that points across it. There is no technology we can currently imagine that bridges it. You are home. This universe, this galaxy, this solar system, this planet, in a way that is final and absolute, not just practically, cosmologically, existentially, and somehow sitting with that thought, really sitting with it, I don't find it crushing. I find it clarifying, because it means that everything we have, everything we know, everyone we love, every piece of music ever composed and every book ever written, and every conversation ever had between two human beings who cared about each other, all of it exists within this one precious bubble. This one improbable, fine-tuned, astonishing cosmic accident, the philosopher and astronomer Carl Sagan wrote in his book Pale Blue Dot, words that have never quite left me since I first read them. He wrote that our planet is a lonely speck in the great enveloping cosmic dark, that in our obscurity, in all this vastness, there is no hint that help will come from elsewhere to save us from ourselves, and that it is up to us, he said. It has always been up to us. I think about that in the context of the multiverse. If there are 10 to the 500th power universes out there, and we cannot reach a single one of them, then this one, right here, with its pale blue dot and its 7 billion curious, struggling, reaching human beings, this one is all we have. And all we have is extraordinary. We are the universe's way of knowing itself. We are the cosmos, briefly awake, looking around in wonder. And the fact that we can ask these questions, that we can peer into the void and map the invisible and chase the horizon of our own understanding, is not a small thing. It is, perhaps, the most remarkable thing. If you are still watching, don't forget to give this video a like and subscribe. It genuinely helps more curious minds find their way here. Let's talk about what deep space would actually do to you. Not in the abstract philosophical sense we've been exploring, though we'll keep that thread alive because it matters, but in the raw, physical, biological sense. Because everything we've discussed so far, the absence of a cosmic center, the dissolution of constellations, the bending of time, the invisible architecture of dark matter, the possibility of other universes, All of it assumes you're alive and functional enough to grapple with the problem. And in deep space, staying alive is its own extraordinary challenge, one that makes every navigation problem we've discussed look almost manageable by comparison. The universe is not hostile to life in the way that a predator is hostile to prey. It isn't hunting you. It doesn't know you exist. It is simply operating according to its own rules, rules that were never designed with fragile, carbon-based, water-dependent creatures in mind. And those rules, played out at their most extreme, produce environments of almost unimaginable violence and lethality. Let's start with the most iconic of those environments, the one that has captured human imagination more than almost any other object in the cosmos, the black hole. A black hole forms when a massive star, typically at least 20 to 30 times the mass of our Sun, exhausts its nuclear fuel and collapses under its own gravity. The collapse is catastrophic and almost instantaneous on astronomical timescales. The outer layers of the star explode outward in a supernova, one of the most energetic events in the known universe, while the core implodes inward past the point where any known force can halt it. What remains is a singularity, a point of effectively infinite density, surrounded by a region of space from which nothing, not even light, can escape. That boundary is the event horizon. The size of the event horizon, called the Schwarzschild radius, after the German physicist Karl Schwarzschild, who derived the solution from Einstein's equations of general relativity in 1916, while serving on the Russian front in World War I, just weeks after Einstein published his theory, depends on the mass of the black hole. For a black hole with the mass of our Sun, the Schwarzschild radius would be roughly 3 kilometers. For the supermassive black hole at the center of our galaxy, Sagittarius A star, which has a mass of about 4 million solar masses, the event horizon stretches across a diameter of roughly 24 million kilometers. That is larger than the distance from the Sun to Mercury. We actually have images of black holes now. In April 2019, the Event Horizon Telescope collaboration, a global network of radio observatories linked together to effectively form an Earth-sized telescope, released the first ever direct image of a black hole's shadow. The target was the supermassive black hole at the center of the galaxy Messier 87, about 55 million light-years away, with a mass 6.5 billion times that of our Sun. The image, a glowing orange ring of superheated gas surrounding a dark central shadow, was one of the most stunning confirmations of general relativity ever achieved. In 2022, the same collaboration released an image of Sagittarius A star, our own galactic center's black hole, a technical triumph given how much more the interstellar gas and dust between us and the galactic center complicated the observation. But what would actually happen to you if you encountered one? The answer depends enormously on the size of the black hole, and it is deeply counterintuitive. For a stellar mass black hole, the kind formed from a collapsing star, the tidal forces near the event horizon are catastrophic. Tidal forces arise because gravity weakens with distance. If you were falling feet first toward a stellar mass black hole, the gravitational pull on your feet would be dramatically stronger than the pull on your head. That difference, called the tidal gradient, would stretch you lengthwise while simultaneously compressing you from the sides. Physicists have a wonderfully descriptive term for this process. They call it spaghettification. You would be drawn out into a long, thin stream of particles long before you cross the event horizon. No drama of crossing a threshold, just a gradual, irreversible elongation into nothingness for a supermassive black hole, however, something with millions or billions of solar masses. The event horizon is so enormous that the tidal gradient across a human body at that boundary is actually relatively gentle. You could, in principle, cross the event horizon of a sufficiently large black hole without immediately feeling anything unusual. You would simply be inside, and from that moment, no matter what direction you pointed your spacecraft, no matter how powerful your engines, every path through space-time leads toward the singularity. Not toward it in the sense of being pulled, but toward it in the sense that all futures inside a black hole point in that direction. Time and space swap roles in a deeply mathematical but physically real sense. The singularity is not a place inside the black hole. It is a moment in the future, and you cannot avoid it any more than you can avoid tomorrow. What happens at the singularity itself remains one of the great unsolved problems of physics. General relativity predicts infinite density and infinite space-time curvature, but infinity in a physical equation is almost always a sign that the theory is breaking down, that you've pushed it beyond its range of validity. At the singularity, quantum effects become dominant, and we currently have no complete theory that successfully marries quantum mechanics with general relativity. String theory and loop quantum gravity both attempt this unification, but neither has produced experimentally confirmed predictions about singularities. What actually happens at the heart of a black hole is, right now, genuinely unknown. It is one of the most important open questions in all of physics. Stephen Hawking added another extraordinary layer to this story in 1974, when he showed, using a combination of quantum mechanics and general relativity, that black holes are not perfectly black after all. They emit a faint thermal radiation, now called Hawking radiation, produced by quantum effects at the event horizon. Over extraordinarily long timescales, far longer than the current age of the universe for any black hole of significant mass. This radiation causes the black hole to slowly lose energy and eventually evaporate entirely. But Hawking radiation raises a deeply troubling question that physicists are still wrestling with. If a black hole evaporates completely, what happens to all the information about the matter that fell in? Quantum mechanics has a fundamental principle, unitarity, that says information can never truly be destroyed. The state of a physical system at any moment in time contains, in principle, all the information needed to reconstruct what happened before or calculate what will happen next. If black holes destroy information, quantum mechanics breaks down. If they don't, if the information somehow escapes in the Hawking radiation, then how? The event horizon is supposed to be a one-way barrier. This puzzle is called the black hole information paradox, and it remains one of the most hotly debated problems at the intersection of quantum theory and gravity. In 2022, significant progress was made when researchers including Jeffrey Pennington at the University of California, Berkeley, and Ahmed Almheiri at the Institute for Advanced Study used tools from quantum information theory, specifically a concept called quantum extremal surfaces, to show that, at least in certain theoretical models, information does escape black holes in a subtle way consistent with quantum mechanics. The full resolution remains a work in progress, but the field is genuinely moving. Now let's step back from black holes and talk about some of the other ways deep space tries to kill you, because they are numerous, creative, and thoroughly unimpressed by human technology: neutron stars. We mentioned them briefly in the context of pulsars, but let's spend a moment with what they actually are, because they are among the most extreme objects the universe has produced. When a star between roughly 8 and 20 solar masses exhausts its nuclear fuel and collapses, the core doesn't quite have enough mass to become a black hole. Instead, it stops its collapse at a different threshold, when the density becomes so great that electrons are forced to combine with protons, producing neutrons and neutrinos in a process called neutronization. What remains is a neutron star, a ball of almost pure neutrons roughly 20 kilometers in diameter, but containing between 1 and 2 times the mass of our entire Sun. Let those numbers sit for a moment. The mass of the Sun, a sphere 1.4 million kilometers across, compressed into something roughly the size of a city. The density of a neutron star is approximately equivalent to compressing every human being on Earth into the volume of a sugar cube. A teaspoon of neutron star material would weigh roughly 10 million tons. The surface gravity of a neutron star is about 200 billion times stronger than Earth's. If you somehow fell onto the surface of one from a height of 1 meter, you would hit with the energy of a nuclear weapon. The magnetic fields around some neutron stars, called magnetars, are the strongest known magnetic fields in the universe, roughly a quadrillion times stronger than Earth's own magnetic field. At a distance of roughly 1,000 kilometers from a magnetar, those fields would be sufficient to distort the electron orbitals of every atom in your body, disrupting the chemistry that makes life possible at a molecular level. In December 2004, a magnetar designated SGR 1806-20, located about 50,000 light-years away in our own galaxy, released a burst of gamma rays in about 0.2 of a second that contained more energy than our Sun emits in 250,000 years. This burst was strong enough to measurably ionize Earth's upper atmosphere from 50,000 light-years away. If that magnetar had been within 10 light-years of us, a cosmic neighbor, by galactic standards, the consequences for life on Earth would have been catastrophic. And then there are gamma-ray bursts, the most energetic explosions in the known universe, releasing in seconds or minutes as much energy as the Sun will radiate across its entire 10 billion-year lifespan. They come in 2 varieties: long gamma-ray bursts, typically produced when a massive, rapidly spinning star collapses into a black hole, sometimes called a collapsar or hypernova, and short gamma-ray bursts, produced when 2 compact objects merge, either 2 neutron stars or a neutron star and a black hole. The merger of 2 neutron stars produces not just a gamma-ray burst, but also gravitational waves, ripples in the fabric of space-time itself, propagating outward at the speed of light. On August 17, 2017, the LIGO and Virgo gravitational wave detectors simultaneously detected gravitational waves from a neutron star merger designated GW170817, while telescopes around the world and in space observed the accompanying gamma-ray burst and its optical afterglow, a kilonova, produced by the radioactive decay of heavy elements forged in the collision. It was the first time a gravitational wave event had been observed simultaneously in both gravitational waves and light, a landmark moment in what astronomers call multi-Schlesinger astronomy. The event confirmed, among other things, that neutron star mergers are the primary source of many of the heaviest elements in the universe: gold, platinum, uranium. The gold in your wedding ring, or your jewelry, or your electronics was forged in the violent collision of 2 dead stars. You carry the universe's most extreme physics on your fingers. Now imagine trying to navigate through a region of space where any of these objects might be lurking nearby. Neutron stars and black holes are often invisible at optical wavelengths. You would not see them through a window. A stellar mass black hole drifting through interstellar space, unaccompanied by infalling material to make it glow, would be essentially undetectable without extraordinarily sensitive instruments. A magnetar could bathe a vast region of space in lethal radiation with no warning. A gamma-ray burst, depending on its orientation, could deliver a killing dose of radiation across thousands of light-years in the brief span of a minute. Deep space is not empty, it is not quiet. At the scales and energies that govern the cosmos, it is churning with processes that make every human construction look as fragile as a soap bubble. And yet, here is where the human connection I keep coming back to becomes most vivid. The same neutron-star collisions that would obliterate any spacecraft that wandered too close are the furnaces that built the atoms of gold and platinum in your body right now. The same black holes that would spaghettify anything that crossed their event horizons are, according to growing evidence, essential regulators of galaxy formation, their tremendous energy output heating the gas that surrounds them, preventing galaxies from forming stars too fast and burning out too quickly. The violence of the cosmos is not separate from its beauty. It is the same thing, seen from different scales. The supernova that scattered iron and carbon and oxygen across our early solar system, atoms that eventually became the Earth, the oceans, the first cells, and ultimately you, that explosion would have been lethal to anyone within dozens of light years. The death of a star made your life possible. That connection between cosmic violence and the existence of everything you love is one of the most profound and humbling ideas that science has ever given us. You are not just observing the universe's extremes from a safe distance. You are made from them. You are the aftermath of events that would kill you if you witnessed them directly. Think about that the next time you look at your own hand. And so here we are, at the edge of everything we know, staring out into a cosmos that has no center, no fixed clock, no visible majority, no guaranteed permanence, and possibly no boundaries at all. A universe where your constellations dissolve with distance, where time bends around your speed, where 95% of reality is invisible, where the very fabric of space is stretching apart beneath your feet, and where the most extreme objects imaginable were built from the same raw material as your bones and your blood. Finding your way home in deep space isn't just difficult, it is, by every honest measure of physics and cosmology we possess, impossible in ways that are breathtaking rather than defeating. Because what this journey through the cosmos ultimately reveals is not how small we are, it's how extraordinary it is that we're here at all, asking these questions, feeling this wonder, tracing the outline of an infinite mystery with nothing more than curiosity and a refusal to look away. We are made of stardust, we are powered by the same nuclear fire that lights the stars, and for one brief, improbable, luminous moment in the history of an ancient universe, we are aware of it, and that, more than any destination, is the most astonishing place you could ever find yourself.